Next chapter, floating and sinking. Now, while studying physics many years ago, my teacher posed this question. A rectangular block floats on the surface of a freshwater lake. A horse jumps on the block, and the block sinks 12 centimeters. How much does the horse weigh? Solving this question makes use of the knowledge of density and buoyancy described by the Greeks over 200 years ago. Before we solve this question, let's talk about floating and sinking. We know that when an object is less dense than a liquid, it floats on the liquid, and if it's denser, it will sink in the liquid. If you try to push a balloon underwater, you will feel a counter force that makes it difficult to push the balloon. When released, the balloon bounces back to the surface. What happens is that the applied force acts in the downward direction, pushing the balloon down. But the water exerts an upward force on the balloon, pushing it up. This upward force exerted on the balloon by water is known as upthrust or buoyant force. When this force is greater than the weight of the object will float. But when the weight is greater than the upthrust, the object sinks. So, why would a small nail sink in water and yet a huge steel ship floats on the same water? The iron nail sinks because it is solid and compact with less volume in water, making its density greater than that of water. So the upthrust exerted on the nail by water is less than the weight of the nail, making it sink. The steel ship floats because it has a hollow space filled with air and occupies more volume in water, making its density less than that of water. So the upthrust exerted by the water on the ship is greater than the weight of the ship, letting it float. Let's get deeper into upthrust by looking at what we call the Archimedes principle. Now, consider a fisherman catching a fish with a fishing line. When pulling the line, it is felt the weight of the fish in water is less than that in air. For instance, the weight in water may be 4 kilograms, and the weight outside is 5 kilograms. And there is also a change in the volume of water. So, two important things here. There is an apparent loss in weight of the fish in water, and there is displacement of water. Now, there is a relationship between this weight loss and the water displaced. Let's find out what that relationship is. We take a Eureka can and a beaker and arrange them as shown here. Pour water into the Eureka can until it overflows through the spout. When the water stops dripping, replace the beaker with an empty one whose mass is known. Suspend a stone with a string on a spring balance and record its weight. Gradually, lower the stone into the Eureka can containing water and record the reading on the spring balance when the stone is completely immersed in water. You will see that the weight of the stone in water is less than that in air. That is, there is an apparent loss of weight. This is equal to 20 minus 17, which is equal to 3 grams. Of course, the stone displaced some water into the beaker. First, we know that the volume of this water must be equal to the volume of the stone. But that is not what we are interested in here. The volume of the displaced water is equal to 3 cubic centimeters. And remembering that density is equal to mass over volume, and that the density of water is equal to 1 gram per cubic centimeters, then 3 cubic centimeters of water will be equal to 3 cubic centimeters times 1 gram per cubic centimeter, which is equal to 3 grams. Incidentally, this is equal to the difference in the mass of the stone in air and water or the apparent weight loss. And this is not a coincidence. It's a fact. It is called the Archimedes principle. It states, when a body is partially or wholly immersed in a fluid, it experiences an upthrust equal to the weight of the displaced fluid. And so, if you think about the ship and the nail, the ship displaces a lot of water and hence experiences a larger upthrust, unlike the nail. Next, causes of upthrust. We'll look at upthrust and pressure. Now, consider a rectangular block of uniform cross-sectional area A, totally immersed in a liquid of density ρ. We know that pressure in liquids is given by H rho g. Let us consider the pressure on the block at two different points. At the top, that is PT, and at the bottom, that is PB. Pressure increases with depth, and therefore PB is greater than PT. In addition to PT and PB, there is also atmospheric pressure, PA, acting on the liquid surface. Pressure PT is the sum of the atmospheric pressure plus the liquid pressure due to height H1. And so PT is equal to PA plus H1 rho g. PB is the sum of the atmospheric pressure and the liquid pressure due to height H2. So PB is equal to PA plus H2 rho g. We know that pressure is equal to force over area, and therefore force is equal to pressure times area. So force at the top, that is Ft, is equal to Pt times A. That is equal to Pa plus H1 rho g times A. And the force at the bottom, Fb, will be equal to Pa plus H2 rho g times A. The resultant upward force, which is equal to the upthrust, is the difference between these two forces. That is Fb minus Ft, which is equal to Pa plus H2 rho g times A minus Pa plus H1 rho g times A. If you simplify that, we end up with AH2 rho g minus AH1 rho g. Factorizing out A rho g, we shall get A rho g times H2 minus H1. From our figure, H2 minus H1 is equal to H, and so we get AH rho g. Again, cross-sectional area times height is equal to volume, and so upthrust is equal to V rho g, where V is the volume of the displaced liquid, which is equal to the volume of the block. And so, the magnitude of the upthrust or buoyant force depends on the volume of the immersed part of an object, the density of the fluid, and the acceleration due to gravity. From this formula, we see that upthrust increases with increasing volume and density. That is why a ship with a large volume floats, while a nail with a smaller volume sinks. If you push two identical pieces of corks into two different liquids, say water and glycerin, you will notice that your hand experiences more upthrust in glycerin because it has more density than water. Let's take an example. A stone weighs 2.0 newtons in air and 1.2 newtons when immersed in water. Calculate A. Volume of the stone and B. Density of the stone. Now, volume of the stone is equal to the volume of the displaced water. We know the density of water is equal to 1,000 kilograms per cubic meter. If we get the mass of the displaced water, we can use density is equal to mass of a volume to find its volume. Let's get the weight of the displaced water. weight of the displaced water is equal to upthrust and is equal to the apparent loss in weight. That is 2.0 minus 1.2 newtons, giving us 0.8 newtons. This is the weight of the displaced water. Converting it into kilograms, we shall get 0.8 divided by 10, and we get 0.08 kilograms. So, how much volume of water weighs 0.08 kilograms? Density is equal to mass over volume, and so volume is equal to mass over density. That is equal to 0.08 kilograms over 1,000 kilograms per cubic meter, which is equal to 8 times 10 raised to power negative 5 cubic meter. This is also equal to 80 cubic centimeters, and this is the volume of the stone. Next is the density of the stone. Density is equal to mass over volume. We take its mass in air, so 2.0 over 10 is equal to 0.2 kilograms. Density will be equal to 0.2 kilograms over 8 times 10 to power negative 5 cubic meters, and that gives us 2,500 kilograms per cubic meter. Next, we talk about upthrust in gases. Now, like liquids, gases exert upthrust on objects in them. The upthrust in air is small owing to its low density, about 1.3 kilograms per cubic meter, but it's still sufficient to make balloons filled with hydrogen or helium to rise. Consider a balloon inflated with air to a certain volume. The weight of air in the balloon plus its fabric is greater than the weight of air displaced by the balloon, since the volume of the air in the balloon is nearly equal to the volume of the air displaced. The upthrust on the balloon due to the air is therefore less than the weight. The balloon rests on the ground due to the downward resultant force, weight minus upthrust. If the balloon is filled with the gas which is less dense than air, such as hydrogen or helium, the weight of the gas plus the fabric is less than the weight of the air displaced by the balloon. In this case, the upthrust exerted by the air on the balloon is greater than the weight of the inflated balloon. The resultant force, upthrust minus weight, lifts the balloon upwards. And so in general, whether an object floats in a fluid or not depends on the upthrust exerted by the fluid relative to the weight of the object. If the weight is less than the upthrust, the object floats. But if the weight is greater than the upthrust, the object sinks. And if the weight is equal to the upthrust, the object will be massed and get stabilized. Let's continue with floating bodies and look at the law of flotation. Now, in order for an object to displace its own volume of a fluid, it has to be fully immersed. How about floating objects? Floating objects still displace some amount of fluid, but not equal to their volume. But there is a relationship between the weight of the fluid displaced and the weight of the floating object. In fact, a floating object displaces its own weight of the fluid on which it floats. It's important you don't get mixed up between the Archimedes principle and the law of flotation. The Archimedes principle deals with upthrust or apparent weight loss for objects partially or wholly immersed in a fluid. The law of flotation deals with the weight of the displaced fluids by a floating object. If the object sinks, the law of flotation does not apply. And so for a floating object, weight of the displaced fluid is equal to the weight of the object. Consider this wooden block which is less dense than water and therefore will float. We first prepare an overflow tank with a spout. Then we weigh the wooden block. It has a mass of 266 grams. We put an empty cup on the scale in a position to tap the overflowing water. We subtract the weight of the cup, so our scale reads 0. When we place the block on the water, it floats and displaces some liquid which runs into the cup through the spout. The scale is weighing this displaced liquid. After some minutes, the flow slows down and finally stops. The scale indicates that the displaced liquid weighs 266 grams, which is equal to the weight of the block. The law of flotation is a special case of the Archimedes principle. It can also be stated as the upthrust force acting on a floating object is equal to the weight of the displaced fluid. Our floating block weighs 266 grams, and the liquid it displaces also weighs 266 grams. Now that we know this, what will happen if we added some weight on the floating block, like this 126-gram stone? The wood block sinks further, displacing more water. And predictably, the weight of the displaced water is 126 grams, the same weight of the stone. Now let us solve the horse question. We have a rectangular block measuring 200 centimeters by 300 centimeters sitting in a freshwater lake. A horse jumps on the block, causing it to sink a further 12 centimeters. What will be the weight of the horse? Like the stone sitting on the wooden block, the horse displaces an amount of water equal to its weight. We need to calculate the weight of this displaced water. Before the horse jumps, the block sits on water at this level. It has already displaced water equal to its weight. When the horse jumps on board, the block sinks a further 12 centimeters. If the volume of water displaced by the additional weight of the horse is a cuboid measuring 200 centimeters by 300 centimeters by 12 centimeters, this volume is equal to 720,000 cubic centimeters. This is the volume of the displaced water. Now we calculate its weight. Density of water is equal to 1 gram per cubic centimeter. So 720,000 cubic centimeters is equivalent to 720,000 grams of water, or simply 720 kilograms. The horse weighs 720 kilograms or 7,200 newtons. The law of flotation is still used today to determine how far a ship will sink when loaded with cargo. The calculation is done just like we have done to determine the weight of the horse. The same is applied in determining how much a hot air balloon can contain in order to float in air. Next, we look at relative density. The relative density of a substance is defined as the ratio of the density of the substance to that of water. That is, relative density of a substance is equal to the density of the substance over density of water. The Archimedes principle can be used to determine the relative densities of both solids and liquids. We start with solids. From the definition, relative density of a solid can also be expressed as mass of the solid over mass of an equal volume of water. Since mass is directly proportional to weight, the relative density can also be expressed as relative density of a solid is equal to weight of the solid over weight of an equal volume of water. And considering that a solid displaces its own volume of the liquid in which it sinks, relative density can also be expressed as weight of the solid over weight of water displaced by the solid. But weight of water displaced by the solid is equal to upthrust, and therefore the relative density of a solid is given by weight of a solid over upthrust on solid in water. To determine the relative density of a solid, the solid is weighed in air and then when totally immersed in water. The upthrust is calculated and relative density determined from the formula above. Liquids. To determine the relative density of a liquid using the Archimedes principle, we take three measurements: weight of a solid in air, weight of the solid when totally immersed in water, and weight of the solid when totally immersed in a liquid whose relative density is to be determined. Since the same solid is used in both the liquid and water, the volume of water displaced equals to the volume of the displaced liquid. The relative density of the liquid is calculated as relative density is equal to upthrust on solid in the liquid over upthrust on solid in the water. And finally, applications of Archimedes principle. Now, the Archimedes principle is used in the designing of ships and submarines. A submarine is a ship that can float on the surface of the sea or sink when necessary. It is provided with large tanks at the front and at the back. These tanks can be filled with seawater or air from compressed air reservoirs. If the tanks are filled with water, the weight of the ship increases and hence it sinks. If the water from the tanks is pumped out by forcing the compressed air, the ship becomes lighter and rises to the surface. Therefore, by filling or emptying the tanks, the ship is made to sink or float. When the envelope of a balloon is filled with a gas lower in density than air, such as hydrogen or helium, the balloon experiences a buoyant force. When the buoyant force is greater than the total weight of the balloon, it is accelerated upwards. A hydrometer is an instrument for measuring the densities of liquids. The lower tip is weighted with lead shots. The stem is graduated with a relative density scale, having unequal divisions and values decreasing upwards. By applying the principle of flotation, the immersed height of the hydrometer decreases as the density of the liquid increases due to an increasing buoyant force.